Hi folks, this is CEO speaking again. Finally, after discussing several times about the XOR gate, we're being able to discuss it using the traditional way, like symbol, formula, truth table, timing chart, and so on. Remember that at this point we have 5 logic gates we already know: the inverter, AND, NAND, OR, NOR. So this is the 6th one, the exclusive OR. Even if there is a package for the exclusive NOR, which I'm going to give you later, the list is consisting of 6 basic logic gates, and this one being the most difficult one. This is why it was taking so long before reaching that level to discuss it in detail. But here we are. So we write it here, the XOR, and I'm going to do at the same time the XNOR gates. A, symbol. Hey, remember we did it in the last couple of videos. What's inside the XOR gate? There are 4 NANDs. What's inside the XNOR gate? 4 NOR gates. Nobody wants in a diagram to draw 4 NAND gates to make that function. But you remember what it is. Okay, so then the engineers, to replace the 4 gates arrangement, the 4 NANDs arrangement, they put that symbol on. It's actually very close to the OR gate. This is looking like the OR gate, but it has one more shield on the left side. So if you put the letters for the inputs, everybody knows, A respectively B, and this one is going to be the XOR. Similarly, for the other one, I'm going to draw it here. It's going to be very similar with the inputs A and B. This output is going to be called exclusive NOR. So these are the actual symbols on the diagram. B, the mathematical function. And here it is. We take it exactly as the formula we established for the what's inside the XOR gate. And I'm going to remind you that is for the exclusive OR. The function equals A times B bar plus A bar times B. You see, that's an interesting combination between these two, because both terms of the equation, they contain A and B. In the first term, B is reversed. In the second one, A is reversed. For that reason, mathematicians invented like a new symbol for that very particular operation. And don't be surprised if in manuals you are going to find something like that. A plus B, but the plus is in a circle. So actually, anytime you see that plus in a circle, it's not an addition. It's that whole thing here. It's just another shorter way to write the one above. So please be careful. As for the XNOR, also discussed in one of the previous videos, is AB plus A bar, B bar. These are the mathematical equations we know. And now we pass to C, the truth table. And I'm going to finally be able to explain where the name comes from. Why is this called exclusive OR? So here, the truth table for the exclusive OR. Remember, the letter X from here and the letters OR from the previous function, XOR. So here it is. We draw a truth table. Same arrangement you already know. We have here the input A, the input B, the XOR is here, and the XNOR is going to be right here. I'm going to build for both functions at the same time because it's easier. Remember what it is for the combinations for the two inputs, A and B. They can either be both 0, or one of them 1, or the other one 1, or both of them 1. These are the only combinations between the two inputs. There is no other way to combine the inputs. And here is the thing. Why it is called the exclusive OR and not just simply the OR, because the OR you know already, okay? Take a look. I'm going to pick up first the lines in the middle. You can see here that the two inputs are different from each other. On the second line, A is 0 and B is 1, so they are different. If they are, the exclusive OR is going to do just the operation you know from the OR. What is the OR? An addition. 0 plus 1 is a 1. Similarly, on the third line, A is 1 and B is 0. So the two inputs are not the same. They are different from each other. 1 plus 0 is 1 again. For this alignment here, as long as the two inputs are different from each other, addition is performed. The problem is, if the inputs are having the same value, either both 0 or both of them 1, the function refuses to do the addition. So it displays just a 0. So this is the reason why it's called exclusive OR, because it's like an OR, is like an addition, with the condition that the two inputs should be different from each other, or else the output displays a 0. So now you know why it is called exclusive OR. As for the exclusive NOR, it's piece of cake. If you know this one, you know the other one because it's just reversed. As you can see here, the two symbols are pretty the same, excepting the XNOR has an inverter connected to the output. So this is going to be 1, 0, 0, and 1. Okay. So here we're going to find out that the XNOR is right the opposite of the XOR. This is why I can explain both at the same time. So, because we know this already, right here, we're going to check it right away, the truth table, on a practical wiring. Just give me a second. I'm going to pick up this one here. And now remember, I have both inputs 0, and the output is a 0 here. I put this input here a 1, this one, take a look, and the output goes a 1, because 0 plus 1 is a 1. I put the other input 1. This one is a 1, and the other one is 0. So the output is still a 1. Now I'm going to put both inputs 1, 1 and 1. What the input shows? A 0. So just to make sure, I'm going to cut the power off. And right here, I'm going to remove for a second the package. As you can see it here. This is going to be one of the two packages containing exclusive OR gates inside. So when I'm plugging it back, this is going to do exactly the job we talk about. When both inputs are 0, the output is 0. If one input is 1, either of them is 1, the output goes 1 because 0 plus 1 is a 1. You see? 1 plus 0 is also a 1. And both inputs are 1, the output is a 0. So that's the functioning on the truth table of the exclusive OR. Similarly, you have an imaginary picture, the timing chart. If you have an imaginary picture of what you see on the oscilloscope, if you had 3 or 4 channels, it would be something like that. Here is the voltage, and I'm going to draw it for the 2 inputs and the 2 hypothetical outputs. voltage is on the vertical and the time is always on the horizontal. So imagine now I'm going to simulate here the two inputs, the two switches. I play with them randomly. This is going to be the input A, this is going to be the input B, and I'm going to do this. So the switch A is in 1 for a while, and then it falls in 0. As for the switch B, it's in 0 for a while, it goes in 1 here, it stays in 1 for a while, and then it falls back in 0. Remember how we do from the previous functions? Any of the inputs switching 0 to 1 or 1 to 0, we drop a line, a vertical one. Because this way we establish the intervals of time synchronized for all the timing charts. And here we just fill the values. From this moment to this one here, the input A is a 1. From here to here is also a 1. And from here to here is a 0. From here to the end, also a 0. So far, so good. Input B. From this moment to here, for the first interval of time, it's a 0. From here to here is a 1. From here to here is another 1. And then it remains a 0. So now, the timing chart just follows the truth table. If the two inputs are different from each other, the output, which is the exclusive OR, displays a 1. If both inputs are the same, the output refuses to do the addition, so it stays a 0. Here the inputs are also different, so the output is a 1. Here the inputs are the same, the output refuses to do the addition. Similarly, for the exclusive NOR, which is right here, is going to be right opposite to this, 0, 1, 0, and 1. So the last thing remaining for us to get a conclusion is to draw the timing chart. Is 1 is up, it is 0 is down, is 1 is up, and 0 down. Similarly for this one, is right opposite, is like the picture you see in a mirror or in a lake. That's it. So you have the axis of time on the right side. You have the voltage on the vertical. So if you know the two inputs, how they vary the values, then you can figure out the outputs, which are following literally what's here, which is the truth table. And finally, E, packages. What packages can you find on the market displaying already these functions? I'm just going to give you the package numbers and I'm going to show you what's inside. So for the TTL, you'll only find a package for the XOR, which is 7486, or if you want 74 LS 86, 74 ALS 86, and so on. All of them, they end with 86. As from the CMOS, classical one, you are going to find 4070. And all this, and you can also say, if you want, 74 HC 86, 74 HCT 86. Okay, I explained these ones much earlier. This is for the XOR. As for the XNOR, there is only one package you are going to find on the market. Don't look for a package in TTL, you won't find it. In the CMOS only, there is a package called 4077. Okay, this one contains XNOR inside. As for what's inside the packages, I have them right here. This is going to be the arrangement for the 7486 quad 2 input exclusive OR TTL. So this is how the gates are arranged if you buy that package. Now, if you have the counterpart, which is the exclusive OR in CMOS, the first gate and the first gate here, they are arranged identically. The fourth one is the same as this one, but the gates 2 and 3 are arranged opposite way. So these packages are not compatible with each other. So don't try to replace the 7486 by 4070. They won't match. Okay. Now, for the exclusive NOR gate, the package 4077, the arrangement is identical to the one in the exclusive OR CMOS. Okay. So don't worry, I'm going to put this one on Google Drive, so you can download the package arrangement. Of course, you can get them from the internet, but it's much easier if I give them to you. Okay, so these two you are going to find on the net. And with this, finally, we finished the description of the 6 basic gates, and the only thing remaining is going to be, can you put this kind of gate on a programmable controller? This is for the next video. Thank you very much. See you next Tuesday. Bye-bye.